All right, this is our beginning of the actual Chapter 2 on polynomial and rational functions. We're going to start with some vocab. A polynomial is a finite sum of terms in the form a times x to the n power, in which the coefficient a is a real number and the exponent n is a whole number. We usually write them in descending order by degree, which is the exponent on the variable. We really care about the leading coefficient, that is the coefficient of the term with the highest degree, and the degree of the polynomial, which is the largest exponent of the function, which should be found on that leading term. We've already talked a bit about quadratic functions, but a reminder that a quadratic function is a times x squared plus b times x plus c. The graph of this is called a parabola. All parabolas are symmetric with respect to a line called the axis of symmetry, and the point where the axis intersects the parabola is called the vertex. We're going to talk about something called vertex form really quick. So our quadratic can be rewritten in vertex form by a method called completing the square, which we didn't really talk about. But vertex form would be a times x minus h squared plus k. The vertex of that parabola is h comma k. If a is greater than 0, your parabola will open upward and the vertex will be a minimum. If a is less than 0, the parabola will open downward and the vertex is a maximum. And the axis of symmetry is always x equals h, which is a vertical line that passes through the vertex.
Excuse the interruption.
So let's try one of these real quick. Given my equation, -1/2 times x plus 2 squared plus 6. Which way does the graph open? Well, I have a negative number in the front, which means it's going to open downward, which also means that my graph is going to be concave down. To identify the vertex, I'm looking for h and k. H is always the opposite of what it seems, so my x-coordinate is -2. My k value is exactly what it seems, so my y-coordinate is 6. The axis of symmetry is a vertical line that goes through the vertex. It'll always be x equals, and that'll be x equals -2. And the extrema, since my parabola opens downward, we have a maximum point. And that maximum will be at the vertex, which is -2, 6. All right, now we're diving straight into section 2, which is polynomial functions of a higher degree. A different definition of a polynomial: let n be a non-negative integer, and let a sub n minus 1, a sub whatever, all those are going to be real numbers, as long as that first one's not 0. The function f of x equals a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power, blah, 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 all the way down to a sub 1 times x plus a sub 0. Just means we have different coefficients and x's to different powers. That is called a polynomial function with a degree of n. The graphs of polynomial functions always have a couple things in common. They're always continuous. There are no breaks like this one has in it here. They have smooth, rounded turns, which means no sharp pointed turns like this graph has right there. So some examples of polynomial functions versus not. This left side, this is a polynomial function. No breaks, only smooth, rounded turns. This one is not. There's a break in the graph. On the left side, I have no breaks and smooth, rounded turns. On the right side, I have a sharp corner, not a polynomial anymore. The simplest graphs of our polynomials will be monomials with a coefficient of 1, such as y equals x squared, which we've dealt with before, y equals x to the 4th power, which is a slightly different looking parabola type shape, y equals x cubed, which is our basic kind of squiggly shape through the vertex, through the origin, y equals x to the 5th power, which is similar in shape to the y equals x cubed. We're going to talk about something called the leading coefficient test. Whether the graph of a polynomial eventually rises or falls can be determined by the function's degree, whether it's even or odd, and by its leading coefficient. Please realize we're talking about whether the degree is even or odd, not the whole function. All right, different uses of the words even and odd. So if the degree is odd and your leading coefficient is positive, your graph is going to go down on the left side and up on the right side. I don't know what it's going to do in the middle here. It's going to do something, but the left will go down, the right will go up. The way we write that is the limit as x approaches negative infinity of f of x equals negative infinity. That part just means the left side goes down. All right? The limit as x approaches negative infinity means the left. This negative infinity means goes down. So then the right side is the limit as x approaches positive infinity of our function f of x. And that goes up, so we say positive infinity. That means the right goes up. If the leading coefficient is negative on an odd degree, it flips everything over. The left side goes up, the right side goes down. In the middle here, it does whatever it feels like. We'll talk about that stuff later. So to say the left side goes up, we say the limit as x approaches negative infinity of f of x equals positive infinity. It's our fancy math way of saying the left side goes up. And we say the limit as x approaches positive infinity of f of x equals negative infinity. Our fancy math way of saying the right goes down. If your degree is even instead, if you have a leading coefficient that is positive, your left side and your right side actually end up both going up. The middle might do whatever it feels like here. I don't know. We say the limit as x approaches negative infinity of f of x equals infinity because the left side goes up. And we say the limit as x approaches positive infinity of f of x equals positive infinity because the right side goes up. And finally, if we have an even degree and the leading coefficient is negative, we're going to flip that last graph over. Both sides will go down. In the middle, I don't know what we're doing. So we say the limits as x approaches negative infinity of f of x equals negative infinity because the left side goes down. And we say the limit as x approaches positive infinity of f of x equals negative infinity. That means the right side goes down. You do have to use this limit notation, and you do have to be able to write it properly. Notice the limit and the x arrow, infinity or negative infinity, is kind of stacked like a fraction, but there's no line between it. The f of x is full size next to that, and then it equals positive or negative infinity. Some pictures that might be a little better than mine, but not necessarily. I personally liked my pictures. Just make sure we use that proper notation. So what does this mean about maxes and minimums? It means that if you have an odd degree, there is never an absolute maximum or an absolute minimum. But you can still have relative maxes and minimums. An even degree absolutely has to have an absolute maximum or an absolute minimum. It'll have an absolute maximum if your leading coefficient is negative. And it'll have an absolute minimum if your leading coefficient is positive. All right, let's practice using the leading coefficient test to determine the right and left behavior of each function. So looking at my first function, I notice that my degree is 3 because that's my biggest exponent. My leading coefficient is -1 because that is the coefficient on that first term. So I have an odd degree, negative leading coefficient. That means the left side goes up, the right side goes down. So the limit as x approaches negative infinity of f of x equals infinity because left goes up. And I need the limit as x approaches positive infinity of f of x equals negative infinity because the right goes down. Yes, you have to have both of those. All right, for h of x, my degree, my biggest exponent, is 4. My leading coefficient, well, there's no coefficient there, so it's just a 1. So I have an even degree, a positive leading coefficient. That means both ends will go up. So to write the left end goes up, I write the limit as x approaches negative infinity of h of x. And yes, on AP Calculus, on the exam, they are very particular. You have to actually call it h of x. If you called it f of x, they will mark it wrong. What we said, this goes up, so it equals infinity. The limit as x approaches positive infinity of h of x. The right side goes up, so it equals infinity. And for number 3 here, g of x, my degree is 5. My leading coefficient is positive 1. So I have an odd degree, positive leading coefficient. The left side goes down, the right side goes up. So I say the limit as x approaches negative infinity of g of x equals negative infinity. And the limit as x approaches positive infinity of g of x equals positive infinity, because the left side goes down and right side goes up. An important note here, the leading coefficient test tells us the end behavior of the graph, but it tells us nothing about what's going on inside. So we have to talk about that. Inside, in between the ends, we will have zeros of our polynomial. For a polynomial function of degree n, the graph of f will have at most n real zeros. So if the degree is 5, we can have at most 5 zeros. We might have less than that. The function has at most n minus 1 relative extrema, which are those local maxes and local mins. So if my degree is 5, I can have at most 4 maxes and mins. Also, please remember, the zeros are the x values when f of x equals 0. All these statements are the same. X equals a is a 0 of the function. X equals a is a solution of the polynomial equation f of x equals 0. X minus a is a factor of the polynomial f of x, and a comma 0 is an x-intercept of the graph of f. All those meant the same thing. So now we're going to find all the real zeros. To find the zeros, we just take our function and set it equal to 0. I factor if I can, so I take out an x because that's my GCF. I have x squared minus x minus 2. Factor what's left, so I have this x hanging out. I get x minus 2 times x plus 1. Set each factor equal to 0, so I get x equals 0. X minus 2 equals 0. Add the 2. I get x equals 2. And x plus 1 equals 0. Subtract the 1. I get x equals negative 1. There are my 3 zeros. And looking at my degree, I see that, oh, I could have had up to 3 zeros. Perfect. To find the zeros of f of x equals negative 2x to the 4th power plus 2x squared, I do the same thing. Set it equal to 0. Factor out my GCF. I'll take out a negative 2x squared, which leaves me with x squared minus 1. Now I factor what's left. So negative 2x squared times x plus 1 times x minus 1. Now notice my degree is 4. I can have up to 4 zeros. Well, my first one, if I set negative 2x squared equal to 0, I just get x equals 0. If I set x plus 1 equal to 0, I subtract 1 and I get x equals negative 1. And I set x minus 1 equal to 0, I add the 1 and I get x equals positive 1. I only got 3 zeros, but I could have gotten up to 4. The reason is because of this squared. Technically, that just means that x equals 0 is a repeated 0. Just means I get like plus or minus 0, which is the same thing. It's just 0. Those repeated zeros are very important. A factor x minus a to the k power, if k is greater than 1, yields what's called a repeated 0, x equals a, of multiplicity k. And multiplicity tells us whether the graph crosses or touches the x-axis at that point. If k is odd, the graph crosses the x-axis at x equals a. When k is even, so your multiplicity is even, your graph touches the x-axis but doesn't quite cross the x-axis. It's important to realize that the graph of a polynomial function can only change signs at its zeros. We can only switch between positives and negatives. Between any two zeros, the graph must be only positive or only negative. The zeros, when put in order, divide our graph into test intervals that help us in graphing. We test the signs of the graph on either side of each zero, and we can get a pretty darn good-looking graph. So that's what we're going to do here. We're going to determine the zeros and their multiplicities. Then we're going to state if those are touch or cross points. Then we're going to determine whether the graph is positive or negative on either side of each zero. So, diving in, this negative 3/5 does not give us a zero, so we're going to ignore it for now. If I set x plus 3 equal to 0, I get x equals negative 3. That has a multiplicity of 4 because that's the exponent on that factor. 4 is an even number, so that means this is a point where I will touch the x-axis but not cross. If I set 5x minus 1 equal to 0, I would get x equals 1/5. This has a multiplicity of 5 because that's the exponent on that factor. 5 is odd, which means that is a point where I will cross the x-axis. So what that means for our graph, I make myself a little number line here. I put negative 3. I put 1/5. My spacing isn't necessarily important here. I'm going to test some number that's less than negative 3. I like negative 4. And I'm going to plug it into my original equation. All I care about is whether it's positive or negative. So I don't really need the actual numbers. I have a negative. If I plug in negative 4 here, I get a negative to an even power though, so it becomes a positive. And if I plug in negative 4 here, I get a negative to an odd power, so it stays negative. So I have negative, positive, negative, which will result in positive. In between the negative 3 and the 1/5, first off, I know at negative 3 it touches. So that means it touches the x-axis and then stays positive on the other side. So I know it's going to be positive, but we'll check. I have a negative times 0 plus 3 is positive, so positive. And I have another negative. Negative times positive times negative makes a positive. I could actually evaluate the value if I wanted to also. And then on the other side of 1/5, let's try f of 1. I get a negative times a positive times a positive. That means it'll be negative. So what that means for my graph is that it's going to do something kind of like this. It'll touch the x-axis, go back up, cross the x-axis. It's kind of the basic shape my graph will have. All right, let's look at the next one. We have 4 terms. Well, we have to actually factor this. And the only way we know to factor with 4 terms is by grouping. Take out the GCF of the first 2 terms. I would take out 4x squared. Leaves me with x minus 1. The GCF of the second 2 terms, or last 2 terms, is minus 25, which leaves me with x minus 1. So f of x is x minus 1 times 4x squared minus 25. And 4x squared minus 25 can factor again into 2x plus 5 times 2x minus 5. Now to get my zeros, I set each factor equal to 0. So I get 1 with a multiplicity of 1 because there's no extra exponent on there, which means this is a cross point. I cross the x-axis at 1 because 1 is odd. 2x plus 5 gives me x equals negative 5 over 2, also with a multiplicity of 1 since there's no higher power here. Since the multiplicity is odd, we cross there also. And set my last factor equal to 0. I get x equals 5 over 2, also with a multiplicity of 1, which means I also cross the x-axis at 5 over 2. If I make my number line here, put these numbers in order, negative 5 over 2, 1, positive 5 over 2. Test some number less than negative 5 over 2. I would probably test negative 3. I'm going to get a negative times a negative times a negative, which makes it negative. Something between negative 5 over 2 and 1, I'm going to test 0. I get a negative times a positive times a negative, which makes it positive in that area. Something between 1 and 5 over 2, I would test 2. I get a positive, positive, negative. So we're negative in that part. And something bigger than 5 over 2, I'm going to go with 3. I get a positive, positive, positive. We're positive in that part. So what that means for my graph is that we're negative, positive, negative, positive, something along those lines for my graph. And 2 more like this. We're going to start off by factoring again. Well, I'm going to take an x out of everything since that's the GCF, which leaves me x squared plus 10x plus 25. To factor x squared plus 10x plus 25, I'm actually going to make it x plus 5 times x plus 5, which I'm actually going to rewrite as x times x plus 5 squared, because now I can see my multiplicity. My first 0 is x equals 0. It's got a multiplicity of 1 because that's that invisible exponent, which means we cross the x-axis at x equals 0. My other 0 is x equals negative 5, coming from that x plus 5. We have a multiplicity of 2, which means I touch the x-axis and don't cross it at negative 5. Make my test intervals, negative 5 and 0. Plug in a number less than negative 5. Let's try negative 6. I get a negative times a negative squared, which makes a negative times a positive, which is negative. Test, I like negative 1. I get a negative times a positive, which is still negative. And let's try positive 1. I get a positive times a positive, which is positive. So this graph is going to look something like this. Touch the x-axis, cross the x-axis, and there we have it. And our last one like this. Again, we are going to take out our GCF first. I'm going to take out a 2x to the 4th power, leaving me x squared minus 7. Well, x squared minus 7 doesn't really factor, but we can solve it. So we get x equals 0 as our first 0, with a multiplicity of 4, which means that we touch the x-axis at x equals 0. When I solve x squared minus 7, I get x equals positive square root 7 and x equals negative square root 7. Oops, that should be a 7. Now I know this was a squared, which makes me feel like the multiplicity should be a 2, but that squared resulted in 2 separate solutions. So each one has a multiplicity of 1, which means each of these are points where we will cross the x-axis. So if I set up my test intervals, I'll have negative square root 7, 0, and positive square root 7. Now square root of 7 is somewhere between 2 and 3. So I'm going to plug in q of negative 3 here. That'll get me a positive times a positive, which is positive. Something between negative 2 and 0 probably. Let's go with q of negative 1. I get a positive times a negative. I would try q of 1 in between 0 and square root 7. I get a positive times a negative again. And I would try q of 3 just to be safe. I get a positive times a positive. There we go. So our graph here crosses the x-axis at negative square root 7, touches, and makes this kind of W-type shape.